Okay, welcome to the 5-1 video notes. Please use the note template to follow along and review the properties of exponents that we talked about at the beginning of the year. Now we're just going to make sure that you really, really absorb them. The names of them, you guys, are not important. It's just utilizing them. That's really the most important thing. The first one is called the product of powers. And the algebraic definition is that if you have a to the m times a to the n, that what happens is as long as the bases are the same, that you keep the base and all you do is you add the exponents together. So a to the m times a to the n equals a to the m plus n. So for example, if you had like x to the 5th times x squared, we keep those bases the same, the base is x, and our new exponent is 5 plus 2, or 7. The quotient of powers means that if we are dividing two powers that have the same base, that what we would do is we would keep the base and subtract the exponents. So if I had x to the 5th over x squared, that would give me x to the 3rd power. You need to be real careful. I see some people like in product of powers, like if you have like 4 cubed times 4 squared, they'll be like, oh, 16. No, okay, that's bad. That's just 4 to the 5th power, and then you can evaluate from there. Okay, so make sure you keep those bases the same. Okay, power of a power. That's when you have a power, like a to the mth, raised to the nth power. What we do there is we keep the base for the time being, and we multiply the exponents together. So if we had x to the 5th squared, that would just give us x to the 10th. A power of a product means that we have a product, like a times b, raised to a certain power. And in that case, that gives me, what happens is we apply that exponent to each of the bases. So a was a factor, so we're going to apply the m exponent to the a base, and we're going to apply the m exponent to the b base. So an example of that is if you have something like 2x to the 5th, each of these are factors. So we're going to apply the 5 to the 2, and we're going to apply the 5 to the x. So we apply it to every single base, every single factor that we see. And then in a case like this, of course, you'd evaluate 2 to the 5th is 32, x to the 5th. So notice it's not, the quantity 2x to the 5th isn't 2x to the 5th, it's 32x to the 5th. So the power of a quotient means that we have a quotient, like a over b, raised to a power. And again, we apply the exponent to both the numerator and the denominator. So if we had like 2 divided by x to the 5th, we would want to apply that exponent to the numerator and to the denominator. And then, as always, if possible, evaluate those numerical powers. Okay. If we have a negative exponent, so if we have a to the negative m, remember what that means is that that negative has to cross through the land of the fraction bar to become positive. On the same token, if you had 1 over a to the negative m, again, that needs to pass through the fraction bar to be positive. So if we had something like 2x to the negative 5th, remember what's being raised to the negative 5th power? Just the x. So this guy has to travel through the denominator, through the fraction bar to the denominator and become x to the 5th. But that 2 was really to the positive 1, so that stays put. So be careful that when you see a negative exponent, you're only applying it like to the specific base it's being applied to. And then the 0 exponent is super fun because anything to the 0 is just 1. So if we had the quantity 2x to the 5th to the 0, that whole thing's being raised to the 0, so that's just 1. Okay, so those are some of the properties of exponents that we will review again. So now let's take a look at some specific examples. There are a lot of different orders that you could do the steps in. If you're looking for an order, I usually like to get rid of the parentheses first by doing the power of a power or the power of a product. And then after that, I like to move any negative exponents. And then I just kind of continue simplifying from there. So like in example 1, the first thing that I would do is I would apply that -2 to both the numerator and denominator. And so when I do that, I need to use the property where I multiply the exponents also. So I have 1 to the -8, and then 3 to the -4. Next, I'm going to move any negative exponents. This guy's got to move to the denominator, and this guy's got to move up to the numerator since they had negative exponents. Then I'll just continue. I'll evaluate. 3 to the 4th is 81, 1 to the 8th is 1, and of course that simplifies to 81. In example 2, this one, we don't have any parentheses to get rid of. And I could move the negative exponent if I wanted. Maybe I'll show you guys this in 2 different ways. But notice here we're just multiplying powers together. So what we could do when we multiply powers is we just add the exponents. So really what we're doing is we keep that base of w, and then we think, what's 5 plus -8 plus 6? And 5 plus -8 is -3. -3 plus 6 is 3. So I have w to the 3rd power. You also could have moved the negative exponent to the denominator and then simplified in the numerator by adding the exponents, and then use the property of the quotient of powers to subtract the exponents. And 11 minus 8 would be 3, which matches what we have over here. Okay, see that? Okay. And again, either one of those steps is fine, as we get the same answer. So in example 3, we'll continue. We'll get rid of the parentheses by applying that exponent to both the numerator and the denominator. Notice here when I multiply d to the -4th, well, when I multiply -4 times -2, I get +8. So then I'm going to move exponents. So this guy's got to move. But notice this guy doesn't have to move. He can stay here. And then if there's nothing left, whoops, we have a placeholder of 1. And then that would be the final answer. 1 over c squared d to the 8th. Example 4, there are no parentheses to get rid of. So maybe I'll just move the negative exponents. So this guy's got to move and become positive, but the b squared can stay the same, and the a to the 5th can stay in the same spot. In my numerator, there's nothing I can really do to that b squared, but in the denominator, since we have like bases and we're multiplying, we can keep the base and add the exponents to get b squared over a to the 8th. In example 5, what I might do is, because there aren't any exponents on the outside, there's nothing to apply to each factor, but I'm multiplying, so what I might do is try to multiply it and squish it like into just one expression instead of a product of an expression. So if I take 7, there are really no other real numbers to multiply that by, so I'm just going to keep that 7. Here, y squared and y to the -4th have the same base, so I can add those exponents to get y to the -2. And then z to the 5th and z to the -1st have the same base, so I can add those together and get z to the 4th. So we did a nice job simplifying that down, except we have this negative exponent. So we think about where that fraction bar would be, and that means that this guy's got to move. So the 7 and the z to the 4th stay, but the y squared will move to the denominator. Now notice that all of our bases are different, and so we know we're okay, and that's our final answer. In number 6, we can apply the exponent first. There are a lot of different ways you could do that, this problem, but that's how I'll start doing this one, is I'll apply this exponent everywhere. And when I apply it to the numerator, notice I'm applying it to every base. Likewise, in the denominator, I'll apply this to every single base. So instead of a squared, I now have a to the 6th. Now I have b to the negative 3rd. Now I have 2 to the 3rd, a to the 9th, and b to the 6th. Remember, if there's an exponent and I'm doing that, I multiply the exponents together. Well, now I'll maybe move any negative exponents. So the a to the 6th can stay, but that b cube's got to, or to the negative 3rd, it's got to move to the bottom and become b cubed. And I'll feed 2 birds with 1 feeder. I'll evaluate this 2 cubed to become 8, and I'll leave the rest of these guys where they are, and notice that that b to the negative 3rd is coming down here. Now I can, don't have any negative exponents, but notice I have some bases that are the same. And so what I would want to do is subtract those exponents. And I know that if you take 6 minus 9, you get a to the negative 3rd. But that a to the negative 3rd ultimately will need to move to the denominator. So one thing we can say is that when you're subtracting exponents, if the power is bigger in the denominator, take the larger exponent minus the smaller one, so 9 minus 6, and then the answer will live where the exponent was bigger. So we could take 9 minus 6, which is 3, and since 9 was bigger, the a cubed will live down here. Now this b to the 6th and b cubed, we can add those exponents together to get b to the 9th. Let's not forget about this 8, and then we have nothing left, so we just have up top, so as a placeholder, we'll put 1. Alrighty. Example 7, again, let's apply this exponent everywhere to every single base that's in the parentheses. So I have x to the 12th, y to the negative 6th, x to the 9th, and y to the 18th. Then maybe move the negative exponents. So these 3, the x to the 12th, x to the 9th, and y to the 18th were okay. But this y to the negative 6th has to cross the fraction bar and become positive. And then here, when I subtract bigger minus smaller, I get x cubed. And since 12 is bigger, that x cubed will live in the numerator. And in my denominator, I have 2 bases that are the same with y. I can add those exponents and get 24. And then I get x cubed over y to the 24th. The bases are different. I can't do anything else. In example 8, if you have a problem where they're multiplying 2 different quotients together, my suggestion is for you to multiply the numerators into one numerator, then multiply the denominators into one denominator, and then go from there. So if you were to multiply numerators, we start with the real numbers. I have 7. Then maybe the x's, I have x to the 1st times x cubed. That's going to give me x to the 4th. Don't forget about that little 1 guy next to the plain x. And then y's, I just have y to the negative 1. So now I've simplified that whole numerator into just one term. Now down in the denominator, I don't have any real numbers other than 1, but I have x squared, nothing to combine that with, and then y to the 1st times y to the negative 4th, so adding those exponents, I'll get y to the negative 3rd. Now again, my suggestion is to move negative exponents when you have these fractions. So those guys were okay, but I'm going to have to move the y to the negative 1 down to the denominator, and y to the negative 3rd moves up to the numerator. And then I have bases that are repeated, so I still have some work to do. The 7 can stay. Notice that 4 minus 2 gives me 2, so x squared will live in the numerator since that's bigger. 3 3 minus 1 is 2. That'll live in the numerator since that's bigger. And then I know there's a 1 down here, but if a 1 is in the denominator, generally we just don't write it in our final answer. So our final answer here would be 7x squared y squared. Okay? So those are the properties of exponents. There are a lot of different ways that you guys could get these answers. You don't have to follow these steps. And then sometimes, depending on the situation, you might want to do it differently, but those are kind of some general rules that you could follow. Okay, so when we talk about the other thing is scientific notation. When we have scientific notation, that is C times 10 to the n, and basically where C, well, let me put it this way, where C is between 1 and 10, okay? So C can be equal to 1 or greater than 1, but has to be less than 10. Once C is 10, then we would want to change it to 1 and move the exponent. You'll see what I mean in a minute. And then n has to be an integer. So remember, an integer means not a fraction. And in scientific notation, hopefully you guys know this, that when we have a positive exponent implies that we have what I'll consider a big number. And I'm going to consider a big number greater than 10. Considering if I have more than $10 in my wallet, that's a fabulous day. And then a negative exponent is going to be when we have a small number. And I'm going to consider a small number anything less than 1. All right? So when we have, let's just work through some of these. So in example 9, we have 3.4 times 10 to the third and 2.8 times 10 to the eighth. So these are positive exponents, so these are very big numbers. Remember what 3.4 times 10 to the third means is that you would take that decimal place and you would move it over 3 places to make it a big number. So that means we would move it over this many places. So that really is equivalent to 3,400. But it's going to be easier for us to use scientific notation to multiply these things. Because what we can do is we know that multiplication is commutative, and basically all of these things are being multiplied together. So what we can do is we can multiply the real numbers together, like this, the regular numbers, the C values together, and take 3.4 times 2.8, and that gives me 9.52. And then I can take my powers of 10 and multiply those together. And since we're multiplying powers with the same base, that means we can keep the base and add the exponents. So I get 9.52 times 10 to the 11th. Then we double check, is this between 1 and 10? And it is. So that's all you had to do in example 9. Okay. In example 10, what we can do is we can take this 5.8 times 10 to the negative 6 to the fourth, and then realize that we have 2 separate bases here. So we would need to apply the 4 to the 5.8 by taking 5.8 to the 4th power. And if I take 5.8 to the 4th power, you would have 1,131.6496. And then if I were to take 10 to the negative 6 to the 4th, remember that that's going to be like multiplying exponents. So that would be like times 10 to the negative 24. Now the issue is that we've done a nice job so far, but this number is not between 1 and 10. To make it between 1 and 10, we would have to move the decimal to this place, and it would have to be 1.1316496. Okay, and notice we moved it over 1, 2, 3 places. Now notice that this was a big number. So since this was a big number that we were changing, that means we're going to change this exponent by 3, but we would need to add 3 because it's a positive because it was a big number. And so then if we take negative 24 plus 3, that gives me negative 21. And so we'll end up with 1.1316496 times 10 to the negative 21st power. Let's talk about another example. In 11, we're going to just start with the regular numbers and divide 4.6 by 9.2. That gives me 0.5. And then if I take 10 to the negative 7th minus 9, that gives me 10 to the negative 16th. Again, by negative 7 minus 9. So, at that point, we notice that this number is not between 1 and 10. We would need to put the decimal here. So we would need to move it over one place. So we need to change this exponent by 1. And because this was a small number, less than 1, that means that we're going to subtract it. So we end up times 10 to the negative 17th. And that would be our answer in scientific notation. And again, the reason scientific notation is nice is because what that means is that this number would have this decimal moved over 17 places. That would be obnoxious to write. It just is something that's so small. So make sure when you're doing these problems in your text that you're checking your answers as you go and double checking that this number is between 1 and 10 and double checking the exponent that you end up with. Iceland covers about 103,000 square kilometers and has approximately 294,000 people. About how many people are there per square kilometer? So when you think about how you would set that one up, people per square kilometer means that we would be dividing those. And so we would want to take 294,000 people and divide it by 103,000 square kilometers. Now humor me, I totally know you could just punch that in, but let's practice how we would write that in scientific notation so you guys get that. Notice to make the number between 1 and 10, we'd have to move the decimal here, and we'd get 2.94 times 10, and we move the decimal over 5 places. And because this was a big number, then this exponent is a positive 5. On the same token, in the denominator, we'd want to move the decimal here to make 1.03. Again, we move the decimal over 5 places, and that was a big number, so that would be positive 5. Now that this looks like the problems in 9 through 10, we'll continue. Again, humor me. So what we can do is divide these two together, and we end up with about 2.85. And then when we subtract these exponents, we can see that we get times 10 to the 0, or you can see that they just cancel. So in this case, what we get is about 2.85 people per square kilometer. And you might say, well, shouldn't we round that to 3? But to be honest, when you're dealing with the statistics, because this is an average about how many people, keep the decimal so that they have that approximation. Okay, 13. A Federal Reserve gold bar weighs 400 troy ounces. What is the weight of 260,000 of the gold bars? When you think about it, if you want the weight of a total, the weight of your total is going to be how many there are times the weight of 1. So there are 260,000 of these, and the weight of 1 is 400 troy ounces. So again, just humor me, and let's write this in scientific notation first. And we end up with 2.6 times 10 to the positive 5, because this was a big number. And then 4 times 10 to the positive 2. And then if I multiply these together, the 2.6 and the 4, I get 10.4. And when I add my exponents, I get 10 to the 7th. But the issue is that this number is not between 1 and 10. So to make it between 1 and 10, I'd have to change the 10.4 to 1.04. And I am going to have to change that exponent by 1. And even though it's not a huge number, it's bigger than 10, so I'm going to add to change the exponent. And so that would be 1.04 times 10 to the 8th troy ounces. And that's scientific notation. And when they talk about the standard form of a number, that's where you take this and you basically turn it into a regular number, not in scientific notation. So we need to move this decimal place over 8 times. That doesn't mean we put 8 zeros on the end. Notice we move it over 2 places, and then we need to move it over 6 more places. So what happens is that we have that 104, and then we add the 6 zeros on the end. And so those are your 2 answers in scientific notation and in standard form. And again, standard form is just regular form. Okay? All right, thank you for filling these out. And then what we'll do is we'll work on the homework in class tomorrow. Okay, thanks guys. Bye.